Okay, so welcome back. Hopefully you were able to get those answers correct. Just as a quick little run through, to find the sum of squares, the variance, and the standard deviation, we just first start off by doing the simple deviation score. I gave you the mean, so all you have to do is figure out how far above or below the mean each of these scores are. So a score of 1 is 3.2 points below the mean, a score of 2 is 2.2 points below the mean. 4 is just a tiny little bit, zero point 0.2 points below the mean. And then our score of 10 is 5.8 points above the mean. So if we were to find the average of this, it would cancel out to 0 after we sum these all up. So not super useful. To make it actually useful, we have to square these deviation scores to get rid of the negatives. So if we square this one, we should get the following answers. You'll notice that these two, which are very close to the mean, when we square them, we're not seeing a whole lot of, too much change. But when we have one like this here, that's 5.8 points above the mean, square it, we get a fairly large score. So it's kind of, in a way, again, getting rid of those negatives and also penalizing us for being very deviated from the mean. So if we were to add these all up, your sum of squares should have been 48.8. We can then plug that into our equations. So our variance is simply those sum of the deviation squared, the sum of squares, divided by the total number of scores that we have. So we have 5. So 48.8 divided by 5 should give you 9.76. Our standard deviation is just simply the square root of that variance. So the square root of 9.76 should be 3.1. So hopefully you all got that. Hopefully that all made sense. And ultimately, again, what this is telling us is that if we look at our scores, here's our mean. On average, our scores deviate by about, with rounding, 3 points from the mean. Now, that's what we will do for our population. Now, I'm going to introduce a slight wrinkle, which is sometimes we are going to be working with a sample. Now, when we're calculating our mean, it doesn't necessarily matter, but when we are working with variability, it actually does. Very quick reminder about samples versus populations. If you remember, population is that complete set of scores. It's basically everybody that's being studied. So for instance, if we were studying Missouri State students, we have about 24,000. So if we were to study the population, we would be looking at all 24,000 students. Or we could be looking at a sample. A sample is simply a subset of those of the population of interest. So instead of getting everybody, what I would do is I would take a subset, say about 500 Missouri State students, and I would collect data from them and assume that they represent the entire population. And the reason why we do that is that, populations are oftentimes either we straight up can't get it. It would be very, very difficult to get everybody from Missouri State to participate in a study, for instance. And, even if we could, it would be pretty inconvenient to do so. And so we usually just do a sample. And, we hope that if we get a large enough sample, that it should, represent the population pretty well. And we can kind of generalize and make inferences based on this sample and kind of assume that, it's the same for the rest of the whatever 23,500 that weren't included. But one issue that we run into, especially when we're thinking about variability, is that, our samples perfect representations of the population? We kind of hope so, we kind of assume so, but when we actually look at it, we see that honestly, not really, especially if we're trying to kind of represent perfectly the amount of variability that's actually present in the population. So, just as a quick example, say I have a set of exam scores. This is scored out of 50 points. And this is for a population with a class of 35 students. So I have every single person's score is represented in this little data set. So if I were to look at the variability in this population of scores, what I would see is that my range would be I have a low of 18, I have a high of 50. So, the range is 32. Pretty spread out, but looking at that. If I were to use my formula, I would look at the mean. find those deviations, square it. If I were to sum that all up, I would get about 1400.74. Divide that by 35, the total number of scores that I have, and my variance would be 40.2. Take the square root of that, and I should get 6.33. So that's what it would be for the population. Now, say I didn't want to look at everybody in the class. Instead, I just take a sample of 10 students. And so maybe I just randomly select, I just draw out of a hat, and I pick these 10 students. So now if I were to look at the variability of these scores, here are my new set of scores. My range now is, my low is this 34 here, and my high is still 50, so my range is 16. If I were to do my new sum of squares, calculate those deviation scores, square it, and sum it up, my new sum of squares is 254.10. You'll notice it's quite a bit lower. Part of the reason that is we have, a lot fewer scores. And again, that sum of squares is calculated by summing everything up. So that's kind of why that difference is there. But even with that in mind, if I were to divide this by 10, I would get 25.41. Take the square root, and my new standard deviation is 5.4. So it's a little bit lower than my population, even when I kind of standardize it and I kind of take into account those numbers. And part of the reason for that is that just by randomly selecting from this overall population, you can see, I left off some of these extreme scores. The low person at 18 didn't get selected. We left off one of these 50s as well. So it's kind of not perfectly representing the population. And part of the reason for this is that it oftentimes excludes those extreme scores. Oftentimes what we see when we look at data is that the majority of scores are going to be pretty close to the mean. And then there's going to be just, a handful of scores that are very, very different. And so when we randomly sample from a population, just by the principle of, things being less frequently occurring, we sometimes miss those extreme scores and we leave them out. And because we're leaving out, those people on the outsides, those extreme, those high deviations, what we usually see is that our variance and our standard deviation are going to be quite a bit lower in our samples compared to the actual population. And that's kind of a problem because we're assuming that our samples are good representations of the population, and we could come away with some misleading judgments if we're leaving out some of these, more extreme scores, or we're pretending that, our scores are a little bit closer to the mean than they actually are. So what do we do about this? What we have to do is we have to make an adjustment to our formula to kind of compensate for this underestimation bias. So if we can make a small little adjustment, what we see is that it ends up actually being fairly similar to the population standard deviation. So how do we calculate standard deviation and variance for a sample? It's going to be the same concept, the same procedure, just with a slight little tweak. So some things to keep in mind. One is that our formulas are going to be slightly different. When we're working with a population, we use Greek letters. So mu for the population mean, the sigma for the population variance. When we're working with a sample, we use, regular alphabet letters. So M for a sample mean, S for the standard deviation, and the variance. So you might see the formulas be a little bit different. But it's still going to be the same principle. We're still working with that idea of deviations from the mean, the average deviation from the mean. So we'll start off with the same principle with the sum of squares. It's literally going to be the exact same thing. You find the mean, you find the deviations from the mean for each of the scores in the data set, square it to get rid of those negatives, sum it up to get your sum of squares. So first step, exactly the same. The variance, though, is going to be where the slight tweak is. So when we determine the sample variance, it's going to be very similar to what we did with the population. We're going to be recognizing that the sum of squares is determined in part by how many numbers we have. So we have to divide by the number of scores in the data set. However, in this case, instead of dividing by the total number, we're going to divide by the total number of data points minus 1. So that's all the adjustment is. We're just subtracting 1 from the total number of scores. So that's where the adjustment is. Then for the standard deviation, it's just the square root of the sample variance. So we take whatever we found in this step, take the square root. So that's the main difference, and that's the thing to keep in mind. First of all, the symbols might be different, and then the denominator for that variance calculation is a little bit different. Now, you might have the question, why n minus 1? Why not just n? Why not, n minus 2? Why not n minus 3? The reason for this is if we just straight up divide by the total number in our data set, it ends up systematically underestimating the population variance. And we don't want that. We want our sample statistics to be pretty much the same as those population parameters. So what we end up doing is when we divide by the n minus 1, it actually adjusts for this a little bit. It kind of helps us recognize like, hey, we probably left off some of those more extreme scores. And what we find is that, if you run simulations, knowing the population and the sample, that adjusting and dividing by that n minus 1, it actually corrects that and actually makes it that sample variance actually be very, very similar to the population variance. And theoretically, when we run those simulations, what we see is that on average, that sample variance is equal or should be fairly equal to the population variance when using that n minus 1. So that's why we use that, and that's something to be looking for when you're asked to do these calculations. Just as a quick summary, here are the formulas for populations and samples. As you can see, the first step, the sum of squares, is basically exactly the same. The only difference is the m versus the mu, but it's the same principle. You're taking the score minus the mean to get that sense of the deviation, square to get rid of the negatives, and then sum all those up. So same for sum of squares. The main difference is this variance step. We're using n, or the total number of scores in your data set, or total number of the population, versus this one here where we have the total number for the sample minus 1. And then we put it together, and basically the standard deviation is just the square root of up here. If you were to put everything together, this would be what the formula would look like. So we have the sum of our deviation score squared divided by n, and then take the square root of all that. For the samples, it's the deviation scored squared, the sum of that divided by n minus 1, and then take the square root of that. So ultimately, that was a lot of math. What are the main takeaways here? Now, this is something that when we work with JASP, it'll do it for us very quickly. However, I do want to spend some time with it, and I am going to have you do it by hand just so that you understand the concept behind it, because this is a key concept in statistics. Both variance and standard deviation are calculated from that sum of the squared deviation scores. So what we're going to see here is with our distribution, if we have lots of scores that are very, very far away from the mean, with this distribution here, we see it's very much spread out, lots of scores that are very, very far away, we're going to see a much higher variance and much higher standard deviations. The average distance from the mean is pretty far away, compared to this distribution here where the scores are tightly clustered. Here, we're not seeing too much variability. the scores are not super far away from the mean. And so we're going to see lower variance, lower standard deviation. The average distance from the mean is not super far away. And so when we pair this with the mean, we're going to be able to figure out a little bit of information about our distribution and how much variability there is. And this will be really important later on when we start to compare means, because if we look, for instance, at the means of two groups, it'll make a difference whether, those scores are, we're comparing two groups where they're like tightly clustered around the mean versus, two groups where they're very much spread out across the mean. So this is going to be very important, not only for descriptive statistics, but for inferential statistics going forward. Another quick summary, just some of the definitions that we learned. So an important thing to understand is the deviation score, which is how much the score deviates from the mean. So the important thing to remember with that is the basis of our standard deviation. That's what we're trying to do. I know it went through, multiple rounds of math and, abstractness, but ultimately what it's looking at is how much each score deviates from the mean. Our sum of squares is the sum or adding up all of the score in our data set's deviation from the mean. Our variance is the average of those squared deviations from the mean. And then the standard deviation is simply the square root. So kind of converting back into its original deviation score notation type thing. And basically what it's telling you is this is the average or the typical amount that the scores in our data set vary from the mean. All right, so that's what I have for today's class. Just as a quick reminder, assignment number 2 is going to be due Wednesday at midnight. Real quick, I will show you a little bit about what that looks like. So a couple things to note. First of all, on homework assignments and exams and stuff, please do note whether I am asking for a population or a sample, because remember, the formulas are slightly different for some of our computations. So what I'd like you to do is, for this set of data, these data points, compute our measures of central tendency and our measures of variability. There are also some questions about, which measure central tendency is best for each type of data. And then there are some short answer questions applying some of the concepts. So that again is due Wednesday at midnight. I'm assuming that we'll probably be back to campus on Wednesday. If not, we'll figure something out. But we can talk about this on Wednesday as well and see if Wednesday at midnight is an okay deadline. If not, we can make some adjustments. Other thing I just want to mention, I mentioned this at the beginning of class, but we'll be starting with JASP on Wednesday. So please do bring your computer to class. If you need to check out a laptop, those are available in the psychology office. And again, please do download JASP on your computer before class so that we don't have to spend too much class time troubleshooting and figuring that out. I mean, I'll be happy to help out, but it'll be a lot easier if we can just roll into it and do it ahead of time. Last thing I want to mention, we'll also have an optional video after this about some Excel tips and how to calculate standard deviation in Excel. That is an optional video, but if you'd like to watch that, that will be available to you. All right, so hopefully I will see you on Wednesday. If not, we'll do the same thing. But yes, let me know if you have any questions. You can also follow along in your textbook. They go into some details and they have a lot of examples that you can walk through as well. So yeah, let me know if you have any questions and stay warm.